All right. So what I want to talk about here is the idea of limits. Because we evaluate functions, but there's some other properties, I guess we might say, that we can explore without even having to talk about a function value. For example, say I've got this function, f of x equals x minus 2 over x squared minus 4. Okay, so yeah, I could plug in lots of different x values, but there are a couple of x values I'm not able to plug into, right? What value, for example, could I not plug in? What value is not part of what we call the domain, the x values that we could plug in here? I could plug in 1, I could plug in -1, but I couldn't plug in 0 would be okay. What I couldn't plug in would be like 2, right? Why not? 2 works on the top, but on the bottom it gives me denominator of 0. And denominator of 0, that's never good, right? You can't have a denominator of 0. Also, the same thing would hold here for -2. We can't plug in -2, but we are going to explore the x value of 2. All right, so x, as far as domain goes, the x's can't be 2 or -2. We could call that our domain, but what I want to do is explore that x equals 2. We'll talk about the -2 counterpart later on, but for right now, let me just talk about some properties or some things that we can look at. X can't be equal to 2, but we can look at some things that go around 2, I guess you might say. Yeah, x can't be equal to 2 because it's not defined. It's a excluded value, we would say. Denominator makes the denominator 0. So that's a lot of times, those are the types of values we're looking at here. Just so happens for various reasons. Okay, so but like I said, I want to look at. Let's look at values around 2 or near 2. Meaning, look at x values around 2, and then their counterparts, the function values around 2, okay? And what I'm going to do is just kind of set up a table here, and you'll maybe see why in just a second. All right, so first of all, all right, so I'm going to look at values around 2. So let me just start, let's just start with 1. Okay, so I'm just thinking about a number line, a value next to 1 here, next to 2 is 1, because that's kind of easier to compute some other things, but we'll talk about that here in a second. All right, so if x is 1, yeah, we can compute x is equal to 1. 1 minus 2 then would be the function value over 1 squared minus 4. Just plug in the x to be 1. And we get -1 over -3, 1/3. Did I do that right? Okay. Yeah, so the function value, the y value then we get is 1/3. All right, now, that's good, but what if I get a little bit closer to 2? All right, so let's get a little bit closer. What value would be closer to 2? Maybe 1.5? So I'm just trying to get x values closer and closer to my x value of 2. All right, so what does that make the function value? Well, it'd be this. 1.5 minus 2 over 1.5 squared minus 4. What is that? -0.5 on top. Is it 2.25 minus 4? Somebody check me. Is that 1.2? Yeah, 1.75. And then divide that by negative. All right. So we got, all right, check that answer first. Yeah, negative 1.7. All right, so negative 0.5 divided by 1.75 is a 0.2857. And this, just for reference here, this is 0.33, of course, repeating. All right, that's fine. That probably doesn't give us much to go on here. But here's the idea. I still want to get closer to 2. So if I want to get closer to 2 than 1.5, what can I look at? 1.6, 1.7, 1.8. Let's kind of jump ahead here a little bit. Let's look at 1.9. That's a pretty close number to 2. All right, so you get the idea here. We're getting closer to 2 without actually hitting 2. All right, so that's 1.9 minus 2 divided by 1.9 squared minus 4. What does that give us? Negative 0.1 divided by whatever that is. Negative 0.3. And so that divided 0.1, negative 0.1 divided by negative 0.39 to 0.25, 641, blah, blah, blah. Okay, I'm just rounding, kind of rounding it here. Okay, all right. Well, now let me go ahead and, because I'm getting kind of tired of computing those by hand, and that's where, you know, graphing calculator comes into play. Yeah, let's utilize some benefits here from having these graphing calculators, because the graphing calculator, one of the things it can do very well is a table of values. It can graph, of course, but right now we're exploring this table, and they do those tables very well as well. Yeah, so I'm going to go to, you go to the Y on the TIs. Does anybody have theirs with them? If not, that's fine. You know, cell phones are great, and you can find a lot of graph, but, you know, for a test, I don't allow you to use cell phones because for various reasons. So be sure to get one of these, and if you need help, just let me know, and we'll try to get it figured out here. But just go to the Y equals screen on the TI-83s I'm talking about there, and enter this in. Now, when you're entering this in, most calculators anyway, what you'll need to do is, I'm going to enter on my Y1, what the first one's called in TIs anyway. You know, to get it just like this, to get the same valued function, you got to be careful, because if I just put in that, what's wrong with that? How does the calculator interpret that? It says, well, I'm going to divide negative 2 by x squared, order of operations, right? It does division. So what I'm saying is, be sure to do parentheses to group the top and the bottom together. That's, pretty hard to do that. All right, just be aware. Okay, get that in there. Get that entered, and then if you go to the table of values, which TIs is just along the top there, above the graphing button, you may have to do a little table setup, because a lot of the calculators are set up, they just give you X values automatically. I want it to ask me what X values to put in, and so just go on the TIs, you go to the table set area, and then on the independent variable, which is the X variable, most often tell it to ask for the independent variable instead of auto, because auto will do probably the integers, but as you can see, we're not going to be doing integers. Okay? All right, so like I said, if you have any questions, just let me know, and we'll get it figured out. All right, so I'm going to check these values. I'm going to put in the 1, make sure I got these right. So far, so good. And like you see, it's a whole lot faster than I am on computing these, and that's what it's basically for, is to help us do something like this. All right, but the nice thing about it is now I can do even more values very quickly, because let's also here, I did leave myself quite enough room, because I'm probably going to do, let's just move over here. All right, so, well, I'll do one more down here just to give this one. So let's do, so I want closer than 1.9 to 2. Well, to squeeze in closer to 1.9, what I'm going to have to do is add another place, go out to hundreds here. And I could do 1.91, but let's go to 1.99, okay? Point 25063. Okay, and let's do one more. So closer to 2, what do you think? 1.99 closer than 1.99? Another 9, right? That would be even closer to 1.99? 9? And we could keep this going, but I think maybe this will suffice. Yeah, it's 0.25006. All right, well, the whole idea here that we're exploring is we're looking at these values. X is getting closer and closer to 2. Right? Those are the X values getting closer and closer to 2. Is there anything then that I can say about the function values as the X values got closer and closer to 2? Well, as those values got closer and closer to 2, and think about this value 2, do you see anything? I'm looking at this one. Can you tell anything about the function value? What's the function value seeming to do here? It looks like that function value is honing in on a value, isn't it? Looks like about 0.25, right? I mean, it's stepped closer and closer every time to 0.25 or 1/4. So the f of x is getting closer and closer to 0.25. Okay? Do we see that? Okay with that? This is the idea of limit. Yeah, we can't get a function value at 2 because the function is undefined at 2. If we plug in 2, the function is undefined. However, as we get closer and closer to x equals 2, the function value does look like it is nearing some value, and it's 0.25. This is the idea of the limit. So we would say, there's a little more we've got to explore here, but it's going to turn out that as x approaches to, x equals 2, the function value is undefined, okay? At x equals 2, f of x equals x minus 2 over x squared minus 4 is undefined, okay? There's no way around that. Denominator is 0, and you just can't divide by 0. However, as x approaches 2, and there's a little more to it, but I'm just kind of giving you a preview here a little bit. As x, it turns out the limit of f of x, the function value f of x equals x minus 2 over x squared minus 4, is 0.25. So even though it doesn't have a value at 2, it has a limit as x approaches 2. Okay? That's the idea. So it's kind of interesting, right? Because I can't plug it in, but this limit's out there. It looks like it's approaching a value. Now, there's some notation and things like that, but I do need to show you that this actually wasn't enough for us to say this yet, because think about the graph here. I'm looking as x approaches 2. And what I've looked at is x is approaching 2 from the lower side. Well, on limits, you also need to look from the upper side, the higher than 2 side, the greater than 2 side. So to complete this table, let's look at the other side of things and see if the same thing happens, all right? But now that we've got the calculator, it'll go much quicker, right? All right, so if I look at this side of 2, what values am I looking at there? Probably 2.1. Let's start there. We could go to, well, let's do 2.1. And 2.1 is 0.2439. Same function. The function value is 0.2439. Function value. All right. Well, okay, so I could go, but let's get closer to 2. So I'm seeing what this limit idea is as x approaches a number. So I want to approach 2. So how could I get closer to 2 than 2.1? Well, I can't do a 9, right? 2.19 would be farther away. No, on this side of things, we're going to have to add in a 0. 2.01. And that's going to be closer. So 2.1's here, the 2.01's even closer. That's 0.24. 938. Now guess what? How are we going to get closer? The 2.01. 2.0. How about 2.001? And then 2. Let's go even one more. All right, so we'll see what those two do. Ah, yes. All right, two good ones. 2.001 is 24994. And then 2.001 is 0.2999. And on the TIs, if you arrow over to the Y1 value on your table, it'll show you even more. This is just showing 5 places. Well, it'll show you at least 10 places, it looks like. But I think that's sufficient. Because as these go to 2, what does it look like these are going to? 0.25 again, isn't it? So the values are getting closer and closer to 0.25. And they're on the other side of 0.25. Those were on the higher side of 0.25, but they were going to 0.25. These are on the lower side, getting closer to 0.25. So that's what I was saying. The limit, you need to look at both sides of things. But I think we've established here a very strong case that the limit as x approaches 2 of this function is 0.25. Now, good news is we don't have to write that verbiage out every time. There's a nice compact notation for this. And here it is. Of course, lim for limit. X approaches 2, we'll use an arrow. X approaches 2. So x arrow 2 is the x approaches 2. And then we can either put the f of x here. You could go ahead and put the expression there. Sometimes you'll see the expression there. But since we've got f of x defined up here, we can just put the f of x, easier to write. But technically speaking, it's this that we're finding the limit of, okay? That equals 0.25. Okay? So that's the idea of limit from a table's perspective anyway. All right, now, one very key point is this. Let's say, I should let my table, but it's all right. All right, so let's say our function is, we're going to define it as a piecewise function, where the first part is the same function, and that's for x not equal to 2. So that's the first piece. And then the other piece is f of x equals, doesn't really matter, 1 if x equals 2. All right, so I've defined this function. Basically what I've done is I've filled in one of the gaps anyway. If x equals 2, the function is 1. So this function, this piecewise function, it's no longer undefined at 2. However, okay, what do you say to the limit as x approaches 2 of my f of x? What would you say that is? Knowing what we just talked about, this limit is what's happening as x gets closer and closer to 2 without actually ever being 2. It doesn't really matter what happens at 2, it's what's happening as you approach 2. So this is what happens as x approaches 2. Not necessarily what it is at 2. That comes into play, but as far as this limit goes, what happens as x approaches 2? Well, what happens to x approaches 2? Well, as x approaches 2, I'm not even considering this. Okay? It's what's happening as x is not equal to 2, but it gets closer. Yeah, as x gets closer and closer to 2, I'm dealing with this function still. And we've already seen what happens to that. As x approaches 2, what does this go to? It goes to 0.25. So it's still 0.25. Because if you think about it again, if I did a table, think about it this way, all right, if you're still not sure. If I'm going to do a table of values and I put in 1.9 here, which of those am I going to use? I'm not going to use this, am I? Because that's only if x equals 2. That's not x equals 2, is it? I'm still going to use this, you see, because it's not equal to 2. And 1.99. And those are going to be the same as before. Is that okay? 0.25 is still the answer there? So, even though so if I ask you then, well, what's the function value at 2? Separate question. So the limit is 0.25 as x approaches 2. What's the function value at 2? It's 1. So, it's kind of weird, but sometimes the function value, well, it happened in the other one too, but a lot of times your function value at 2, or wherever you're approaching, x is approaching, it may not match up with the actual limit. Kind of a little, takes a little getting used to. Okay? So yeah, those two are separate. All right, now let's do another one. Okay, so let's say I've got limit x approaches 0 of sine of x over 3x. Sine of x over 3x. So let's evaluate this. Let's use a table. That's all we know right now. We're going to get a few other ways in a moment. Okay, so in this case, we've got to interpret what we're doing here. We're limit as x approaches 0 sine of x. So if I use a table here, x, and then the f of x is here, we call it that. First of all, as x approaches, so what values am I going to use? 0 is a little different than like 2 or the other integers. If I want to approach x as 0, what values should I use? So I want to approach x equals 0. Think about the graph here. I want to approach x to be 0. So I need to do both sides. So if I approach, let's just do the right side here for the greater than side of 0. What numbers would I use to approach 0, I think, here? Well, if I'm on this side, maybe 0.5, 0.6, something close to 0. But let's just cut to the chase. Let's get even real close to 0, 0.1. Let's start at 0.1. Go ahead and put that in my, again, be sure to use parentheses around that. And then the other thing I might mention, since I'm doing a trig function here, if you don't get these values, be sure your mode is in radian mode, not degree mode. We want sines of radian angles. Anyway, so what we should get for 0.1, I went to the wrong thing there. All right, table. All right, so put in 0.1, and I get 0.33278 for first value. But I want to approach 0, so I want to get closer to 0. So that's where I want to add the 0, right? 0.01. And it gives me, 0.333. And then if I go to 0.001, I think we'll see already this what's going on. It's also 0.33. And like I said, if you want some more values to those, this is actually 333.277, and then this is 0.3363s, and then 277. So you can see we do get more threes there. But yeah, I think we kind of see as x goes to 0 here, these are going to what? Well, it looks like they're going to keep repeating 0.3 or 3333. What number is that? Does anybody know the decimal? What fraction leads to a decimal 0.333? Repeating? It's 1/3, isn't it? Yeah, those are going to 1/3. 0.3 repeating? Yes? Okay. 1 divided by 3 is 0.3 repeating. All right. Now, I'm not yet ready to say, though, that this limit is 1/3. Why is that? Because, like I said, for this to work, this table thing to work, it's got to be both sides. For this to be 1/3, because the next example, the next example I show you, they're going to be different on one side and the other. So you do have to check both sides. So I do want to go ahead and look at the other side of things, approach 0 from the less than side of 0, which on zeros, what you have to do there, of course, is go to the negatives, and you're just going to do the negative 0.1s. Negative 0.1, and then closer would be those. Okay? All right, so let's see. See what happens. Negative 0.1, negative 0.01, negative 0.001. And I think, yeah, these so happen they're the same values. Sometimes that happens. Yeah. So not only from the greater than side of 0 does it approach 1/3, but the function value, but also on the lower, less than side of 0. Same thing happens. So yeah, this limit strong evidence that limit turns out to be 1/3. Okay? Question? Agree with that? All right. So yeah, let's. So I got a couple of other examples, and then got a couple of other things, but all right. So the limit as x approaches 0. The absolute value of x over x. So we're approaching 0 again, so it's the same idea, still use a table here. And let me go ahead and mention, when you're doing these particular problems on your homework, be sure to list the table. Don't just tell me the answer, because if you get the wrong answer, I don't know. You don't have the table there, I don't know what you did. Okay, so show your work. I'm big into show your work on homework, please. Not just this one, but others. But on this one in particular, show me your table. Okay, show the table here that we're going to use. We'll look at other processes for doing this, but for right now, show the table here. And so again, I'm approaching 0, so I'm going to use those same values. They work pretty well for that one. Now this one, you don't have to plug it in the calculator. You can if you like, but you may not need to. Some of them are easy enough. Here, this one might be one of those. Well, let me just go ahead and mention, we will graph some absolute values, so I'll go ahead and mention. On the TIs, the absolute value function is called ABS, and on the TIs it's under the math menu. So if you can find the math menu, or you can just look through the catalog and find ABS for absolute value. That's how you would enter it in. But like I said, I don't think we really need to do that here because it's so simple. It's just the absolute value of x, so it'd be negative 0.01 absolute value, divided by x, so it'd be divided by the x. What is that going to do? Well, that's going to be positive 0.1 divided by negative 0.1. You got negative 1 there, don't you? What's going to happen here? Same thing. Guess what happens here? Same thing. Okay. But the limit here is not negative 1 because we've got to look at the other side. What does the other side do? F of x is the absolute value of x. So on the other side, I'd be looking at the positives. What are those values going to give? Positive ones, aren't they? Because when I do the absolute value divided by just the x value, I'm no longer dividing by, it's a positive divided by a positive. So those are just all going to be 1s, aren't they? Yeah? Uh-oh. These go to negative 1, or they are negative 1. These go to positive. The two don't match. So if the two sides don't match, then what we say here is this limit doesn't exist. D and E, you'll see that they may, in the book, just put D and E does not exist. And if you do that, that's fine too. But just stresses the fact that, yeah, both sides, the limit has to match. Okay? Now, what we can do on this one, and the other ones, but this one is in particular one good to do this, is we can say, well, we have a limit on this side of negative 1, we have a limit on this side. Well, again, going back to the graph here, it's a right and left thing, is how on limits we explain it. When we're these x values are x values on the left of 0. So what we say is the limit of f of x from the left is negative 1. Okay, and here's how we write that. The limit as x approaches 0 from the left, and we're going to use a little superscript there, just of a minus sign. And so that'll tell me, I'm focusing on 0, but from the left, okay? This means 0 from the left. So x approaches 0 from the left. So that limit is negative 1. Well, guess what? This table over here tells me the limit from the right is positive 1, and so guess what that symbol is? Well, if you're approaching 0 from the right side, or whatever number it is from the right side, the greater than sign, use a plus superscript or exponent. Look kind of like an exponent, but you know what I mean. So that means 0 from the right. So that limit, based on this table, is positive 1. Okay? Now, also, I know I'm throwing a lot of information here at you, but hopefully it'll soak in. We said it, but one thing, when you tell me something doesn't exist, why? So going back to this one, all right, so these limits, this limit from the left is -1, this limit from the right is +1, but this limit right here, same function, but this limit doesn't exist. Why? Well, now we have a nice way of saying this, because the limit from the right doesn't equal the limit from the left. And we have a good way to write that. The limit as x approaches 0 from the left of the absolute value of x does not equal the limit as x approaches 0 from the right. So if I ask you to explain, or the book asks you to explain, that's a nice way to do it. Because that tells you everything you need to know. For this limit to exist, the limit from the right has to equal the limit from the left. So the limit doesn't exist if the two do not equal. Okay? All the other previous examples, the limit from the left and the limit from the right were equal. Okay. Okay. Now, let's look at this from the graphing side. So we looked at it from the table perspective.